Now this is 10.4, page 284, and the difference is that 10.5, the next section, will be at a changing speed. So this is constant speed, in other words, no acceleration. Now let's consider a simple case of something travelling at constant speed. Now you can't really talk about taking off from the lights in a car, because even though you get to constant speed pretty quickly, there is a period of acceleration. The best one could be, let's say you're running to catch the bus, and I'm not talking about when you started, but you're running at a constant speed. Now let's say you had a time and a displacement. Now really it should be constant velocity. I've said in the book constant speed, but I'm going to really talk about velocity. So let's say my time in seconds and my displacement in meters is something like this: 1, 2, 3, 4, 5. Let's say your displacement is 0 at the beginning. After a second, let's say you've moved 10 meters, 20, 30, 40, 50 meters. Okay, now we're going to draw a graph of that and then have a look at the characteristics of the graph. So here's my graph. Now I'm going to do 1, 2, 3, 4, 5 and a 0. This is my S, my displacement, and the unit is meters. And I'm going to do, no it's not, that's time rather, sorry, time in seconds. And this is going to be my displacement in meters here. And I'm going to do 10, 20, 30, 40, 50. Now this is pretty rough. Whoa, 20, 10. In the textbook, I've done this nice and neatly so it's easier to see. Okay, let's plot these points. 5 seconds, oh let's start here, 0. Now when you're doing this by hand, we use a cross, just so that when you draw a line over the top of it, the cross, if you use a dot, you can't tell where the point was, where the marker was. If you're using Excel, make sure you use a dot that's big enough to see. And Excel by default does it big enough, just so long as you choose one that's got the dots on it. So 1 second it's 10, 2 seconds it's 20, 3 it's 30, 4 it's 40, and 5 it's 50. Okay, now I can draw a straight line through that. I haven't got a ruler, but you get the idea. There's a straight line through that. It's not very straight. A straight line through that. Now if you think about it, the question is, what's the average velocity? Let's have a look at some of the characteristics of this. The V average is just S on T, so it's 50 over 5, which is 10 meters per second. Now we're not worried about the direction. I haven't told you about the direction. The other thing is the displacement, the S equals 50 meters after 5 seconds. Okay, so if you talk about a journey, now let's imagine this is from somewhere 50 meters to the bus, like I was saying, but you're going at constant speed. Well, you could be running somewhere, but you're already moving when you started measuring the speed. The journey has been 50 meters and the average speed has been 10. Now the question is, what characteristics of this graph match up with the 10 and the 50? Look, I'll get rid of that, it's confusing. The first thing I'd like to work out is the gradient. Where have we got room here? If you look at the gradient, is now it's change in y, so it's delta y over delta x. So change in y is from 50 to 0. So final minus initial. So the final y value is 50, the starting y value is 0. So that was final minus initial for the displacement, and the final minus initial time is that. So that's 10. So the gradient of, this is called a ST graph. The gradient of an ST graph is 10, which is its velocity. So it'll have the symbols ms to the -1 because it's S divided by time. And I said to you before, that's just s divided by metres divided by seconds. Okay, so I'm going to write this down in a minute, and I'm going to say the gradient of an ST graph is the average velocity. Okay, the second thing we can look at, now I'll get rid of all this, we don't need it. The second thing you can look at here is the area under the curve. So we look at the area. So I'm talking about this area here. So that's called the area under the curve. Now I know it's not curved, but it's called a curve. It's just a straight curve. Now the area, it's a triangle. So area equals base by height on 2. So the base is 5. The height is 50 over 2. And that comes to, what does that come to? What? 125. Something's gone wrong. What? Base by height on 2. What have I done wrong there? 5 seconds. The area, that's not right. The area is nothing. Cross that out. The area of a, what am I doing? The area of an ST graph is nothing. It doesn't mean anything. Don't tell anyone I did that. That's a mistake. I'll give myself a mistake. Look, I'm thinking of the next type of graph. The area would be S times T, and there's no unit ST. We don't use anything that has a formula, something equals displacement times time, so it's nothing. So we can sum up by saying the gradient of a ST graph is the velocity. So I'm just going to write this down. So this is what you'd write. You'd say the gradient of VL. Okay, so that's about all there is to that. So if you saw a graph like this, T rather, versus S, and it looked something like this. Okay, let's imagine it looked like that. Now you could work out the velocity at the different stages. We could call this stage A, stage B, and stage C. Now this could be, I think in the book I've said a dog chasing a cat or something like that, but the dog goes at constant speed for a while. The question is, what's the dog doing here? And the answer is there's no gradient. The gradient is 0, so the velocity is 0. So the dog has run, stopped for so many seconds, and then has run back to the start. So it's run, you could imagine running up to the letterbox, standing there for a few seconds, but running back to the house or running back to where it started really quickly because the gradient is really steep. So slow, stopped, fast. Okay. Look, I think I might leave it there. There's not a lot else to say. I think what I'm going to do, I might do the velocity time graph. So I was going to break this up into 2 lessons, but I think we can do this now. Look, if I said to you, let's do, that was displacement time. Let's now do, look, I'll put it here. One was displacement time. The second one is going to be velocity time. So I'm going to look at graph of constant motion, but I'm going to have a look at, it's still going to be constant speed, but I'm going to look at the velocity. Now the question is, what's the velocity of the person every second? Now in the first second, the person's covered 10 meters per second. So the velocity is going to be 10. 10 metres in 1 second. The velocity from here to here is going to be 10 in 1 second. So from there to there is 1 and so on. So 10, 10, 10 metres every second, and there's the 1 second. Okay, so if you plotted the velocity versus time, so in the first second you do it like this. Right, the first interval, the person, remember, wasn't starting at rest. They had no displacement at rest. They were at the 0 mark. So what they're doing is they're running. They hit the 0 mark while they're moving at a certain speed. So, and you know it's the velocity of 10 and it's metres per second. Okay, so 10 there, and so on. Okay, so now this makes more sense. This is where I was getting trapped. So the graph of a velocity time, the velocity time graph for a thing travelling at constant speed will be a straight line, and there's no change in velocity. Okay, so that's all you can say about constant speed. Now, if it's a if it's a fast constant speed, like 10 metres per second, it's there. If it's only 1 metre per second, like this, it'd be down here. But it has to be a constant motion, covering the same distance every same unit of time. Now, what we can say about this, there's two things. See if you can get this. Now, the gradient of that line, the gradient is change in y divided by change in x. So it's still the same old formula, but if you think about it, there's no change in y. It was 10 there and 10 there, so it's 10 minus 10, if you like, which is 0. The change in x is 5 minus 0, so that's 0. The gradient of that is 0. Now the question is, what's the gradient of a VT graph supposed to mean? Now the answer is 0. So what's 0 about this motion? And the answer is the acceleration is 0. The person is not accelerating, they're keeping the same velocity. So the gradient is the acceleration. Now that makes sense when you think about it. Look, v divided by t. You learnt, hopefully you learned in grade 10. Now that unit in grade 10 was a good unit. It was written a couple of years ago, and it's been updated since, of course. But the formula for acceleration, now I don't know how you wrote it down, but it was basically change in v on t, or you might have written v minus u on t, something like that. Okay, so change in velocity over time is acceleration. So v divided by t is acceleration. So the gradient of a VT graph is acceleration. Okay, I'll write that down as a summary in a minute. Now, this is where I started to tell you something, and I realised I was making a mistake, but I was happy to own my mistake. Nothing wrong with making mistakes. The area under this, now if we work out the area, let's have a look. The area is just 10 times 5, which is 50. Now, if you multiply these two, and well, I'll do it this way. What did we know about that motion that was 50? And we knew that the displacement at the end of the journey was 50. So it could be that this area under a VT graph is displacement. Now if you think about it, area is length by breadth. So if you multiply meters per second, which is this thing, times seconds, they cancel out and you're left with meters. So the unit for that is meters. Okay? I'm going to sum that up. So look, I'll just do this again. I'll make a nice little summary of these two graphs, and that's probably all you really need for this. So how will we do this? We'll call this a ST graph and a VT graph. So that's the type of graphs. Let's call this the gradient, and let's call this the area under. That's area under the curve. Now, this is how this will work. I'll use a better pen. Whoa, that's not very good. Do you mind if I do it in... I'll do it in blue. Blue seems to work reasonably well. Okay. The gradient of an ST graph, if you remember, was the velocity. The area under... the gradient of an ST graph, yeah, was velocity. The area under an ST graph, I started to work that out, got myself into a tangle, or realising I'd made a mistake. That means nothing. The gradient of a VT graph was the acceleration, which was 0 in the case of constant speed, and the area under was the displacement. Okay, so let me just sum up with using graphs as well. Now, if you looked at a graph of T versus S, and you did T versus V, this is what you got. ST, you got a straight line like that. Okay. For a VT graph, you got that. Okay. And in that case, it was at 10. This case here, it was getting bigger and bigger. Can I ask you this now? It'll save doing it later. If I said to you, what do you think an AT graph would look like? What would you say? Now, this is constant speed, remember. We're not talking about accelerated motion. That's the next chapter. The acceleration here is 0. 0 acceleration. It's not getting any faster. So this graph here would look like that, right on the 0 point. Okay, so that's a T. Those three graphs go together. Now in the next chapter, we're going to look at accelerated motion. So V will actually be increasing. So that'll be the difference. The tricky thing, what happens to S? So if this line is going to go up at an angle like that, what on earth is this thing going to do? Is it going to curve one way or the other? And what's this going to do? But that's the next section. Look, I think I've done all of that. I did talk about non-constant velocity, but that's accelerated motion. Now I've put it in here as a worked example just to show you how to do the gradients of a curve, but I might leave that till the next chapter. It fits in better. So that's about it. You're able now to do these CYL questions. I don't think you can do... There's one question which has a curve in it, but I'd leave that out. That's question 3, it looks like. You could leave that out till we've done the next section of our work. Okay, I think that's about it. So that's it. Thank you.